In this video, we will learn about the skewness or asymmetric nature of distribution. This is a distribution and this perpendicular line has been drawn from the peak point over this x-axis. It is clearly visible that this perpendicular line is dividing the whole curve into two equal halves, and these two halves are congruent. That means symmetric. So if you can place a perpendicular line from the peak point on the x-axis so that the curve can be divided into two halves, then that distribution is a symmetric distribution. Now, this green distribution is tilted somewhat towards the right hand side, isn't it? This distribution we say as negatively skewed distribution. And the red one is our positively skewed distribution. That means in the red distribution and the green distribution, we see some skewness or asymmetric nature which was not present in the blue distribution, isn't it? So you may say that this blue distribution is symmetric and the red and the green ones are asymmetric distribution. That means these two distributions are losing some symmetric nature, right? Now see another positively skewed distribution, and we name this distribution as D1, this one, and this one as D2. So D1 and D2, these two distributions both are positively skewed distributions. That is, they are asymmetric, but the measure of skewness is somewhat different. See, D1 is more skewed than D2. Now, how you say that D1 is more skewed than D2? Actually, you are comparing this D1 and D2 with the symmetric distribution, this blue one. So, to measure skewness of a distribution, you always take a symmetric distribution as your reference. Clear? So, the skewness is a measure of how much the distribution is asymmetric. Let's look at this table. This table is talking about some donations done by some persons. Okay. Now these are the denominations. 10 rupees was donated by one person, so we have written 1 here. 20 rupees was donated by 3 persons, so we have written 3 here. And you can see that this 10 is the middle point of this list of numbers. And above 10, the numbers appear like this: 631. And on the other side, you have 631. Now, if we get the visualization, it will look something like this. This is the x-axis. There's a donation amount. And this side is your donor count, that is your frequency. And you will get this. That means 10 rupees was donated by one person, so this line is there. 20 rupees was donated by 3 persons, so the line goes up to 3. And this one is 30 up to 6, 40 up to 10, like that. And if you join these data points, then you'll get a figure like this. Now this is a symmetric distribution. Why? Because you see this perpendicular line on x-axis, what we talked about before, that this line is dividing the whole curve or the whole distribution into two halves or two congruent halves. See, on the left hand side of this perpendicular line, you have the point at 6. On the right hand side also, you have the point at 6. You see this left one at 3, right one at 3. On the left one, you have the point at 1, here also at 1. So you can clearly see that this is a purely symmetric distribution. Let's go with this table, and this table is talking about the rainfall. Now, if you measure rainfall in millimeter, then you cannot have the exact figure of rainfall, right? So what we do, you go with class intervals. That means for how many days there was rainfall between 0 millimeter and 10 millimeter. So there is only one day, so you have written 1 here, and the interval is 10. Clear? The next one, from 10 to 20. For how many days the rainfall was between 10 to 20? Actually from 11 to 20 millimeter actually. So we have the interval here 10, and we write here 3 days. In this way, we get the day counts or the frequencies like this. And here also you can see that this is the midpoint, this is the middle point actually, this 10. And on one side you have 631 and on the other side you have 631. Now, to handle this class intervals, we have to go for frequency density. Now, what is frequency density? It is nothing but the frequency per unit interval. That means you have 10 millimeter as your interval and you have a day count 1. Then for 1 millimeter, what will be the day count? That means 1 by 10 or 0.1. Now the question is why we are going for this frequency density. The intervals here is a constant. That means every time all the classes have equal width, that means 10, right? But when we will have the intervals of unequal width, that means this is 8, this is 10, and the other one is 4, like that, then you have to bring the frequencies of the unequal widths to a standardized interval, right? Generally, our standardization goes with 1, as we do in unitary method. For example, say you have 8 apples, and these 8 apples will cost you 160 INR, right? Now, if I ask you, what will be the cost of 5 apples? What you do? You take one apple, and how much it costs? Say 160 by 8, that means 20 INR. So you get the rate of the apple, of each apple, that is 20 INR, right? Now, if I ask you what will be the cost for 5 apples, then you can clearly say that 5 times 20, that means 100 INR, right? So what you are doing in this unitary method is that you are bringing down this 8 to a standard value of 1 from where you can go anywhere you like, to 5, to 15, to 200, anywhere, any number you can go from this 1 apple data. Clear? So the same thing we are doing here also, but since we have the interval equal in this list, then you will not see the exact utilization of this frequency density. After this, we will take another table where we will have unequal interval, and there you will see the usefulness of this frequency density. Okay, so let's continue with this this table. So here we go with the frequency density. That means 1 by 10 will give you 0.1. That means each millimeter is having a frequency of 0.1 day. Okay, the second one, for each millimeter you have 0.3 days, right? So this is actually the rate, or the frequency rate. Okay, so let's see on the figure. This is the rainfall and this side is our frequency density. Here you will find the 0.1, 0.3, 0.6 and 1.0. These are the 4 data points we have in this list. So the other points are not mentioned here. Now this is your first class interval, that is 0 to 10, and it will go up to 0.1. The second class interval goes up to 0.3. The third one 0.6, fourth one 1, and it will go like this. So here also you can see that this is a symmetric distribution, right? Now we have a table where the class widths are unequal. You see, the first class interval is 1 to 4, that means the interval is 3. The second class interval is between 4 and 15, and you have the interval as 11. So the intervals are not same here, and you have the day count 1, 3, 6, 10, 6, 3, 1, just like this. And you have the frequency density like this, because here you need the frequency, because sometimes this day count is talking with an interval 3, and sometimes this day count is talking with an interval 11. So the interval actually varies. So based on this varied interval or the unequal interval width, you cannot have a clear idea actually that which one is higher and which one is lower, right? So just like the unitary method example, that apple example we saw before, in the same way you have to standardize the interval and the day count. So if the interval is 3 and the day count is 1, then you go for 1 interval, that means 1 unit. There is a 3 unit, there is a 3 millimeter, there is a day count is 1. So you have for 1 millimeter how many day counts? So here you go 0.3. Here you see the second one. For an 11 millimeter interval, you have a day count 3. So for each millimeter, what will be the day count? This is 0.3. So all the rows of unequal width is having an uniform rate here. That means this frequency density, this column is talking about frequencies based on unit interval. Now you can compare which one is higher and which one is lower, right? So frequency density is more useful when class interval widths are unequal. Now here we go with the figure. This is a rainfall and this is a frequency density. And the first class interval goes up to 0.3. The second one, you see it is much wider than the first one and it also goes up to 0.3. Third one goes up to 0.5 and like this. Now we can clearly see that the day counts were symmetric. See, this one is 10, here is 631 and on the other side you have 631. But when you have this frequency density, that means the rate of day count per millimeter, then the distribution becomes asymmetric, right? Well, we have enough idea to deal with the measures of skewness. Now we start with the symmetric distribution in detail. So here we go with the table, the previous table we have seen before. Now, how will you know exactly that the distribution is symmetric? You calculate the mean. And for calculation of the mean, you need the total donation amount, right? So 10 rupees was given by one person. So this row gets 10 in total. This row 20 rupees was given by 3 persons. So you get 60 here. In this way, you get all the total amounts in each row. And this 1200 is a grand total. That means this amount has been collected from 30 persons. You add these frequencies and you will get the total number of persons or the total number of donors. So there are 30 donors in total. And from those 30 donors, you have got 1200 in total, right? So the mean donation amount will be summation of fi dot xi by summation of fi. So this is 1200 and this is 30 and you get 40. So here we go with the mean, that is it is standing at 40, right? Now we have to go with the calculation of median donation amount. For calculation of median donation amount, you need this additional column, that is cumulative frequency, right? So what is cumulative frequency? This 1 is initially added with 0. This original frequency is here and you add 0 to get this 1. And then you add this 1 to this 3 to get this 4. Then 4 plus 6 will give you 10. This 10 plus 10 will give you 20. Then 20 plus 6 will give you 26, like that. And you will get the cumulative frequency. And the last value of cumulative frequency will be the total number of persons. Because every time you are adding the data, isn't it? That means you are updating the summation. Naturally, this last amount or the last figure of this cumulative frequency will be the value of n or the value of the frequencies. Value of the summation of frequencies, right? So, mean donation amount is the value corresponding to the summation of f by 2th cumulative frequency. Now, this we have learned before when we are learning median. If you missed the video, then you can check the description. I have given the link. Now, this summation of f will give you actually n. So, n by 2th cumulative frequency, that is 30 by 2, that is 15th cumulative frequency, and it will give you 40. Why? Because you see, this 15th cumulative frequency is not there. That is from 10, it is going straight to 20, right? Now, in our previous video, we have learned that if you do not have your computed cumulative frequency in this list, then you will take the next higher cumulative frequency. So, our computed cumulative frequency is 15, but 15 is missing. So, the next higher cumulative frequency is 20. So, we will consider 20 as our cumulative frequency, right? and the value corresponding to 20 is 40. So our median is 40, right? So we go 40 here, this green one. Next we go for the mode, and this is the value corresponding to the highest frequency. Now you see this list. The highest frequency is 10. The corresponding value to the 10 is 40 here. So we have the 40 as the mode here. That means you can see in a symmetric distribution, the mean, the median, and the mode all are placed in the same location, right? So mean is equal to median is equal to mode, and the left tail and right tail are also equal. So we get a symmetric distribution. Now we start with asymmetric distribution. Here is your table, and the donation amounts are like this. You have the donor count and you have the total donation here, and you get a curve like this. Why? Because you see here, 10 rupees was given by one person as before, so it is 10. And you see this 20 rupees was donated by 10 persons, and you get 200 rupees in total. In our previous table, this 20 rupees was donated by 3 persons, and this frequency was gradually increasing up to middle point, and then the frequency was going down in the same manner to the last row. But here you see, from 1, the frequency suddenly jumps to 10, and after 10, it gradually goes down to 1, right? That is why the figure is going like this. So this is a skewed distribution, more specifically positively skewed distribution. Okay. Now here we go. We have the total frequency 30, and you have the total amount collected from these 30 persons is 990. That means it went down from 1200 to 990. Why? Because more people donated lower denominations than before. So the mean donation amount will be the same formula, and you will get 33. So here you go with the 33. Previously it was 40. Now it has gone down to 33. You see, the mean this time has shifted towards the left. Now we have to go for median, and for computation of median, you need this column, that is cumulative frequency, and the same formula, summation of f by 2th cumulative frequency. Here also the 15th cumulative frequency you will get, but here 15th is missing. So you can see that from 11 it is going straight to 19. So we take the next higher cumulative frequency, that is 19, and the corresponding value is 30. So your median is standing at 30. And mode is the highest value corresponding to the highest frequency. So highest frequency is 10, and you have the corresponding data as 20. So your mode is standing at 20. Now if you draw this perpendicular line like this, it is clear that it is not able to divide the whole curve into 2 equal halves. That means wherever you put this perpendicular on this x-axis, you will never get a location from where you can divide the whole curve into 2 equal or 2 congruent halves. And that indicates that this curve or this distribution is asymmetric. So the right tail is longer, this tail. We get a positively skewed distribution. Here you can see that mean is greater than median, greater than mode. That means mean is standing here, that is 33. Median is at 30 and mode is at 20. So you can clearly see that mean is more than median, which is more than mode. Now we have this skewed distribution where you can see that more people are donating with higher denominations. That means 60 rupees was given by 10 persons, 50 rupees was given by 8 persons. And that gives you 1410 rupees in total. So the collection goes high. So for the mean calculation, the same formula, and you will get 1410 by 30, that is 47. So 47 is here. For calculation of median donation amount, you need this cumulative frequency, And here also 15th cumulative frequency. 15th is missing. That is from 11, it is going straight to 19. So you will consider the 19th cumulative frequency and the corresponding value is 50. So your median is standing at 50 now. And your mode is standing at 60 because 10 is the highest frequency and the value is 60. So here you go with the 60. And if you draw a perpendicular line anywhere, whether here or anywhere, you will not get a proper location from where you can divide the whole curve into two equal parts. And this also clearly indicates that the distribution is asymmetric. And it is also negatively skewed distribution because the left tail is longer. And here the mean is the lowest and it is lesser than median and the lesser than mode. So in a positively skewed distribution, the mean is highest and mode was lowest, and here mean is lowest and mode is highest. So here is your figure. You can compare if you want. You can pause the video and see what these things are looking like. And you notice one thing, that median is always between mean and mode. Not in symmetric distribution, but in case of skewed distribution or asymmetric distribution, you have this feature that median is always between mean and mode. You see, this one is mean, this one is mode, and median is between these two. Here also, this one is mode, this one is mean, and the median is between these two, right? In a negatively skewed distribution, among these measures, mean is the lowest and mode is the highest. And in a positively skewed distribution, mode is the lowest and mean is the highest. Now the question is, what is the difference between variance and skewness then? Because we see that the skewness is a measure of the variation, right? So the variance, what we learned before, tells us about the amount of variability, while the skewness gives the direction of variability. Criteria required for a good measure of skewness. First criteria is that your measure should not be dependent upon any unit. Because if you change the unit from centimeter to millimeter or like that, then the value may change. The second criteria, if the distribution is symmetric, then the value of the measure should be 0. Similarly, the measure should give positive or negative values if your distribution is positive or negative respectively. That means for positive skewness, your measure should give positive value, and for negative skewness, your measure should give negative values. And the third one, and the last one of course, if you move from extreme negative skewness to extreme positive skewness, then the value of the measure should vary accordingly. That means the value should change. It will not remain stagnant at any location, right? That means if you have an extreme negative skewness, and it will look like this. If it is extreme negative, and this skewness is moving towards positive skewness, that means positive skewness will be, extreme positive skewness will be like this, right? So it is moving towards this figure to this figure. Then the value of the measure, what you are actually following, must change. Now here is a table with which we will deal with the measures of skewness using moments. Now you have learned already that moment is nothing but mean of deviation, right? Now whenever you have a deviation like this, that xi minus x bar, of course this is a deviation, and you sum up and you divide this summation by n, then you will get a moment. And this is a moment about mean of order 1, because the power 1 is here. Now if you give the power 2 here, that means a squared deviation, then this becomes your variance, right? You have deviations about arbitrary point also. That means you replace this mean with some arbitrary point A and you get a deviation, right? You can have this arbitrary point as 0, which is also called raw moment. So if you missed the video, then you can check the description below. I have given the link. Now let us concentrate on this one. You see, odd ordered central moments. Now what is central moment? The moment about mean is central moment, right? And what is odd ordered? That means the power is either 1 or 3 or 5 or 7, like that. Okay? Now see, when we have the central moment with order 1, then the value of the moment will always 0 for any skewness of the distribution. And that makes this central moment of order 1 useless. But the central moments, odd ordered central moments of order 3 or above will help you to have a good measure of skewness. That means M3 will work, M5 will work, M7 will also work. In this way, you can go higher and higher. Why these are useful? These are useful, right? Why? Because whenever the value of the moment is positive, this M3 or M5 or M7, then you will have a positively skewed distribution. And for negative value of this moment will be there if your distribution is negatively skewed. And this moment will give you 0 whenever you have a symmetric distribution. And that conforms with the criteria, right? Now, which one should you use? This M suffix 3, M suffix 5 or M suffix 7? That means this M3 is actually of order 3, this is order 5, order 7, order 9, order 11. Which one would you use? That is a question. The point is, you can see that we have already discussed that whatever the order may be here, any odd ordered except order 1, it works. But if you have a higher order moment, then your computation will be much costlier. That means you are making the system more complex. So for simplicity, we will take the minimum one, that is the moment, that is the central moment of order 3. Now you have a table of these absolute measures and relative measures. In case of absolute measure, you may have the skewness like this. You subtract mean and median like this, mean minus median, and you will get a skewness. Also, you can get a skewness if you subtract mode from mean. And the third way, third quartile minus second quartile minus second quartile minus first quartile. So any of these 3 absolute measures you can have for getting the measure of skewness. But there is a problem. In distribution with small variation or in a distribution with large variation, the same amount of skewness has different meanings. And for this reason, these absolute measures of skewness will not work. So we move to relative measures of skewness. The relative measures are called coefficients of skewness, which are pure numbers, and these numbers are independent of units, which was a problem with the absolute measures. Okay, so we will go with the relative measures for an effective measure of skewness, right? There are 4 common relative measures of skewness. The first one is beta and gamma coefficient of skewness. The second one is Carl Pearson's coefficient of skewness, Bowley's coefficient of skewness, and the fourth one is Kelly's coefficient of skewness. The video is getting longer, so I will stop here and I will make 4 more videos each of these measurements. Okay, so the next video will deal with the number 1, that is beta and gamma coefficient of skewness. And I hope up till now what we have discussed is clear to you.